Okay, this is adding forces that are not collinear. There isn't too much to this. It's not as difficult as it might seem. Two methods. This is the parallelogram method. I've drawn the steps here. Draw two rays parallel to the existing forces. So what that means is we've got F2 here. So I'm going to draw in a ray that's parallel and the same magnitude, because these vectors are drawn to scale if you want to do this correctly. If we're going to end up with the resultant that's the correct magnitude, we need to keep things to scale. So that's our first ray, F1, and it needs to be the same length as F2 and at the same, needs to be parallel. So these two need to be parallel. Okay, and then we draw the second ray, which is F1. So that's our F1 ray. And then all we need to do to get our resultant is draw the resultant force from the intersection of the forces to the intersection of the ray. Well, this is the intersection of the forces that's being applied, and the intersection of the ray is over here, and we just draw our resultant in. Now I'm going to label that FR for resultant force. So that's our parallelogram method. That's a good method. The other one we have is our triangle method. So basically what happens is whenever we're adding these forces that are not collinear, we need to get the magnitude right and the angles right if we're going to do a graphical solution. So we can take our F2 and we can imagine that we're taking the whole of that F2 vector and we're transposing it. Okay, we're moving it up so that it goes, the tail of this goes to the head of this, because we add tip to tail to get our resultant. So when we move that F2 arrow up here, okay, so now F2 is here, because I've shifted it up, same size, same angle. These two have to be parallel, okay, because it's just F2, so all I've done is add it to the tip, to the head of F1, okay, so move it up. We can get rid of F2, okay, and then the resultant, of course, is from here to the tip of this arrow, okay, that is FR, and you can see it should be the same, okay, angles are slightly different because the angles weren't drawn the same, but those two methods are essentially pretty much the same, just a different way of thinking about it, okay, so you can either move that force up, go tip to tail, or draw the two rays parallel to the existing forces and draw a resultant, okay? Over here, we have an extension of this triangle method where we're adding head of arrow to tail of the other one, okay? But we've got more than one force here. So what you can do is you can take our first force, they're all being applied at the same point, so they're concurrent. So we're going to go F1, we need to draw it at the same angle and the same magnitude. Then we go, well, what's F2 doing? We're going to join it here, and F2 is like this. So that's F2, and then we go F3, we're sort of leveling out, and it's shorter than F2, it's F3, and finally we go F4, going down but very small. And how do we find our resultant? We go from where we started to where we finished. Our resultant would be that vector there, FR. Okay, so just adding tip to tail, okay? That is how you do non-collinear, okay, coplanar forces. So we now should know how to do collinear, we should know how to do addition of forces that are not collinear, and you will be putting all of these skills to use in later problem solving, okay? When we're doing truss analysis and all that sort of stuff, you need to understand how to resolve forces, how to find resultants, all that sort of stuff. And this is the theory behind that, okay? So by all means, pause the video here. Make sure you write down all of these notes, okay? How we arrive at our parallelogram method, our triangle method, and of course polygons of forces. Now, the interesting thing with this situation here later on when we find out about equilibrium is if all the forces cancel, okay, that polygon will be closed. In other words, you won't be able to get a resultant because the final force will be come back to a point of origin. the polygon or triangle is closed, when we add all of the forces together, it means that we have a situation that's in equilibrium. In fact, I think you can close a triangle, sorry, if the polygon is closed. Okay, so, because if you have two forces, no matter how you add them, they're never going to close, okay, unless they're doing that, in which case they'll be in equilibrium, but they're not forming a triangle, are they? So, closed polygon, system in equilibrium, resultant is 0, okay? But for this situation here, we ended up with quite a large force, and that's the angle as well. If we draw it to scale, and we draw our angles correctly, we can measure that. If we know our scale, we can calculate that force, and we can measure its angle from the horizontal, theta, and we can quote that as well for direction. Because whenever you quote a force, you need, because it's a vector, you need magnitude, you need sense, and you need direction. Okay, the sense is the arrow. Direction is this angle here from the horizontal, and magnitude is the length of the arrow. We should know that from when we studied vectors. Anyway, that's it from me for this video. Hope that's helpful. Definitely take the notes down and have a crack at some addition of